Okay, so hopefully you didn't need a calculator for the first column. Root of 1 is 1, root of 4 is 2, root of 9 is 3, root of 16 is 4, root of 25 is 5. So if we keep going in order, the next perfect square is 36, then 49, so that'll be 6 and 7. Now in your calculator, so as I said, you don't need a scientific or you don't need a graphing calculator. You can use a scientific. And so we're going to go 1 to the exponent 1/2. So you just go 1 divided by 2. That's 1. Nothing changes. Then 4 to the exponent 1/2. What do you get? 2. Then 9 to the exponent 1/2. So you're just letting your calculator do it. So you need to know where your exponent key is in order to do this. If you don't have an exponent key on your calculator, you need to get a calculator that has it. But for today, share with your neighbor. Okay, it's either the up arrow or it's y to the exponent x or x to the exponent y. So then 16 to the exponent 1/2. What's the pattern here? Are you getting the same values as taking the square root? Yes. Okay, Seth, you got to get your stuff out. Okay, so yes, you are. So we'll fill that in. Cubed root, again, cubed root of 1 is 1. You don't need a calculator. Cubed root of 8 is 2. If you're not sure, go back to that chart in your notes. We did all of these. Perfect cubes. Cube of 27 is 3. Cubed root of 64 is 4. 125 is 5. Then, so 6, 7, we would fill in here. So 36 times 6, what is that? I always forget. 216, 343, yeah. Okay, now, you might not know where the cubed root is on your calculator. Matei, question?
Explain to me how, like, when it's the exponent of 1/2, why does it?
Yep, we're going to do that if you look at the question underneath. We're just finding the values right now. So here, cubed root in a graphing calculator, and very similar, graphing calculator, somewhere where the math functions are. So in a TI, we go math, and the fourth one down is cubed root. Okay, and then we know the cubed root of 1 is 1. Let's put 8 in there. Okay, we get 2. So that's where cubed root is, if you weren't sure. If we're doing 8 to the 1/3, then that's just the exponent key. Okay, so we're getting 2. If we do the next one, that's, what is it? Oh, sorry, I put it in the wrong place. The wrong row. That was 1. This is 2. So then cubed root of 27. 27 to the exponent 1/3 is 3. Same thing's happening. Should give you an idea of what this fractional exponent means in terms of a radical. Oh, I put the wrong thing. 125, not 1255. Okay, I get 5. So the pattern is that these two columns are exactly the same. So if we think about that, that means that this is equal to this. This is equal to this. So from the tables above, what can you conclude about an exponent of 1/2? It is the same as taking the square root. Okay. Exponent of 1/3, same as cubed root. Okay, because those two right-hand columns of each chart were exactly the same. So sometimes we might show a radical as an exponent. Sometimes we might show an exponent as a radical. And we can only do that if it's a fraction, right? Hudson, phone away, please. So let's look at 1/2 in more detail. Use your exponent laws to simplify the following. So powers with the same base, doesn't matter what kind of exponent it is, what value, you add those exponents. So it's really 1/2 plus 1/2. Well, what's 1/2 plus 1/2? It's 1. 6 to the exponent 1 is 6. Okay? Using radicals from what we just learned, raising to an exponent 1/2 is the same as square root. So square root of 6 times square root of 6. Well, think about that. That's the same as questions we did. That's the same as root of 6 times 6. So 6 is a repeated factor. It's really 36 if you expand it out, and the root is 6. So again, it doesn't matter if it's in exponent form or radical form. These mean the same thing. Square rooting is raising to the 1/2. So what do you think exponent of 1/4 means? What's another way of showing it? That's right. 4th root, exactly. The little 4. Okay, oops, that got a little squish there. And some of you on the quiz forgot for cubed roots, the little 3. Okay, it changes the value when you forget that. Okay, so test this theory by evaluating each without a calculator. So what you could do is go, okay, I'm taking the 4th root of 16. Okay, well, hopefully you remember that 2 to the 4th is 16, or you can do a factor tree and you get 2. Now, if you want to use powers to check this, exponent form, then remember 81 is 3 to the 4th. Okay, so we could replace the 81 with 3 to the 4th. It's raised to the 1/4. Multiply, oops, that's not what I wanted to do. Multiplying, we got to multiply the exponents when you're raising a power to a power. So 4 times 1/4 is just 1. Okay, so you can do it either way. So in general, we always like to have a general rule like we did on the first part of the notes the other day, 2 days ago when we reviewed Math 9, is we had the rules split out. So a to the 1/m, we're going to fill this in. I'm just going to make my pen a little thinner. It's going to be mth root of a. Okay. Okay, so extension of that is maybe we have a fraction, but the numerator of the fraction isn't 1. So here, all we did when it was 1, we took the m, and that was the root. But now we might have something like 2/3. Okay, well, let's go through our power laws. Is, when we simplify this, is 1/3 times 2 the same as 2/3? You got to remember your fractions. Yeah, because it's 2 over 1. So yes. And what law is that? That's the power of a power. Okay, so from there, if we think back to our radicals, we could say, okay, that's cubed root of 8 all squared. Now, if we were to evaluate that, cubed root of 8 is 2. 2 squared is 4. Okay, now look at this expression on the right there. So we have that cubed root of 8 all squared, and we're saying that it's the same as the cubed root of 8 squared. So that squared can be outside the radical or it can be inside with the radicand. It doesn't matter. So sometimes it's easier if it's outside because then you're keeping the number inside smaller, and sometimes it's easier for you on the inside. Yeah, sign out, please. Okay, again, the rest without a calculator, these two here, verify with one. So, oh, we just did this one, so that's kind of silly. We should have given it different. So here, I've got it up there, but that's the cubed root of 8 squared. So that's 2 squared, which is 4. So that numerator is actually an exponent on the radicand, whether you put it in with the radicand or outside the whole radical. So here, this would be 4th root of 16, and then cube it. You could show it like this, but do you really want to do 16 cubed? Like, I don't know what that is. So that's a pain, right? Easier to do this. I know 4th root of 16 is 2, and then cube that is 8. We can check it if you want. So it says to check with your calculator. So let's check that second one there. So it was 16 to the 3/4. Okay, got 8. If we do the cubed root, so math, and then go down to cubed root of 16, cursor out, and then raise to the exponent 4. Oh no, sorry, 4th root. I got to fix that. So now we need 4th root, right? So math, 4th root, I better teach you on your calculator, is exp root. They don't have a 4th root key. So when you enter that, you actually put the little 4 in there, cursor to the right, then put 16, cursor out of the radical, and then exponent 3. And notice what the calculator just did on the TIs. It took my exponent 3 on the outside and put it on the inside. Either way, it means the same thing. That's a clue. You could use brackets like I did on my work. Bracket, 4th root, bracket, math. Got to be careful, it's sensitive. There. Now I have 2 brackets. Okay. 4th, I'm going to go delete one of those brackets. There. Cursor inside. 16. Cursor out. Close the bracket to the exponent 3. Okay. So same thing either way, inside or outside. Okay, turn over to the next page where it summarizes what we just did. So if we have a to the m over n, that's like taking the base and raising it to 1 over n, then raising that to the exponent m, power of a power. Okay. In radical form, that would be the nth root of a raised to the exponent m, all raised, or the nth root of a to the m. So that m exponent can be inside or outside. So I want you to complete the table below. You're just showing, you don't have to evaluate or anything. You're just showing radical form, exponential form for each. And I'm going to get at my Casio calculator. So if you have a Casio and you want to do a cubed root, go to math and, oh, maybe not math, arrow. No, you don't even have to do that. Okay, so exit on that. No. For Casio, you go into shift, bracket, and that's cubed root. If you want a 4th root, you go shift, exponent key, and you can see it there. So then you enter the 4th root of 16, cursor to 16, and that would be 2. Okay, so that's in a Casio. You don't have to go into a math key at all. Struggling. The root is the denominator of the exponent. memorize it. You need to. So the root, the cube, the 3 is the denominator of the exponent. The exponent on the radicand is the numerator. The 4's stay the same. The big numbers stay the same. The small numbers stay small. It's where you put those small numbers. So -8 is the radicand. The denominator is 3, so it's cubed root. Here, leave the negative out. It's outside the radical anyway, right? So then it's 27. The root is 3, so it's 1/3. Here now, the radicand is 81. The root is 4. And you can either put the 3 inside or you can put it on the outside. Here, the negative has nothing to do with that power. Remember, there's no brackets around it. So I'm going to put negative. And then the radicand is 4. The root is 2. Do we need to show a 2 for a square root? No, because it's so common. So really, I can erase that little 2. No. Okay. And then 5 is the exponent. Now, myself, oh, that gets messy. I like to have brackets personally, but that's just me. So I'm going to just make this a little neater and say, okay, square root of 4, square root of 4. To the exponent 5. Okay. But you can put the 5 inside. But you cannot put -4 inside. You can't take the square root of -4, and that negative is not in brackets. Okay, here it even has the radicand in brackets. So 64 over 125. So I'm going to keep it in brackets. The root is 3, so that's the denominator, and it's squared, so that's the numerator. You're just moving the numbers around, and it means the same thing. William? Yeah, quickly, go sign up. Okay, then here, there's brackets. So in the root, I put everything that's in brackets. You can even keep the brackets if you want, or put that all in there. Then the root is 3. Now, if I'm raising that to the exponent 7 inside, I need brackets inside. If I'm doing it outside, I'm going to put it outside. So really up to you. If I keep it on the inside, why don't we keep it? Then it's really easy. You're just copying the entire bracket inside the radicand. Oh, 7. Yeah, right. If it was cubed, it would just negate itself. So 7 there. Okay. So without using a calculator, evaluate. So all the ones above, we were just showing it in a different form. Now we're finding the value. Write the answer as a reduced fraction if necessary. So here, sometimes you will find it's easier just to convert to a root. So if it's 1/2, that's the root of 64. That's 8. If you want to convert 64 to a power, you can. I think it's easier to remember root of 64. But when you get into more complicated expressions as you go on in math, you might end up using powers much more frequently than roots. And the next one, this would be square root of 16 cubed. Well, square root of 16 is 4 cubed, and 4 cubed is 64. Okay, I'll show you the alternative if you used powers. One possible, there's more than one because 16 has choices, but we could show 16 as 4 squared to the 3/2. Then power of a power, 2 times 3/2 is 3. And then we get 64. So really the same number of steps, 3 steps, but just the first one's different. Are you going to convert to exponent form, or are you going to use radical form? So if we use radical form here, it's the 5th root of negative 32 cubed. Hopefully you're starting to remember that 2 to the 5th is 32. So negative 2 to the 5th is 32. Is negative 32, I should say. And then we're cubing it. So a negative cubed is negative. Okay. So cubed root of a negative is negative. I'm sorry, the 5th root, any odd root. And then when any odd exponent on it, when whoever gets back, just when William gets back. Okay. Then here again, cubed root of 64 over 125. Okay. And then we're going to square it. Yep, that's 4 over 5 squared. See, 4 over 5 is 16 over 25. Nope, that's it. Can't reduce it. Okay, there's nothing in common because there's nothing in common in that base. So you're done. Okay, so anytime you have a decimal in the exponent, if you're asked just to find the value, you could punch it into your calculator. Okay, but yeah, you can go. It's back. So in terms of this notation and converting, we need a fractional exponent to do the conversion. Okay, so here, this is 32. What's 0.2 as a fraction in lowest terms? Hands up, hands up. Okay, Seth. 1/5. So here, this is 1/5. So now we're doing the 5th root of 32, which I already said from the third one, that's 2. Okay, so you don't need a calculator. You doing this? Okay, 0.75. What's that as a fraction in lowest terms? Yeah, 3 over 4. It's Nevin, right? Yeah. 81 is 3 over 4. Okay, so you don't want to put 75 over 100. Well, you can, but you got to reduce that. Are you going to take the 100th root of something? Don't think so. So here, this is going to be the 4th of 81, 4th root, cubed. Okay, so that's going to be 3 cubed is 27. Okay, so listening please just for a sec. Notice how in all of these when I was evaluating, I put the numerator on the outside because then I'm dealing with smaller numbers. I didn't need a calculator. If I put 81 cubed inside, then I have to figure out what 81 cubed is and then take the 4th root. Well, that's a waste of energy, right? So think about the process that you're using. Oops, sorry. Keeps flipping here. Just a sec. All right, now these have variable bases. So we're not evaluating anything. These are almost easier, okay? So our radicand is the variable. That's the easy part. So here, the radicand is x. We just have to decide on what root it is. The numerator is 1, the denominator is 4, so it's the 4th root. Here, the radicand is y. The denominator of that exponent is 3, so that's the 3rd root, and it's squared. Now you can put the squared on the outside or in the inside. Remember, it doesn't matter. But with variables, it's kind of nice to have that exponent on the variable inside. As opposed to numbers, I kind of liked it on the outside for evaluating. Okay, here, A is the radicand. The base is the radicand, right? The base of the exponent. The denominator of that exponent is the root, and the numerator is the exponent on the radicand. either inside or outside. Okay, and then 0.4 ends up, what's 0.4 as a decimal, as a fraction in lowest terms? Vincent? Vincent. 2 out of 5, yeah. So this is 2/5. Oh, that's not a, sorry, I put a 4 there. It's a W. Okay, so then we have root W, where the root is the 5th root, and we're squaring the W, either inside or outside. Okay, so I want you to do question 5. Now you're converting from radical to exponential form. Okay, so I'm just going to show for the video purposes at the end. I didn't turn my, so check, people watching the video, check your answers. Okay, now we'll get going on this. So part B, evaluating this, it's got a negative exponent. So this is, I'm going to switch to a thinner so I can fit it in. So that's going to be 1 over negative 32 to the 2/5. Notice I caught everything else looks the same. It just goes into the denominator. The negative exponent tells you denominator. Okay. Then evaluate this. So that's 1 over, that's going to be the 5th root of negative 32 squared. So that I think we did 5th root of negative 32 on the previous page. It's negative 2 squared, which is 1/4. Negative 2 squared is positive 4. Again, right now, for some of these, you can check with your calculator. Okay. Next one, it's a fraction. So fractions, brackets around the whole thing. So we just flip it. Notice how I did not flip 1/4. The negative in the exponent flips the base, not the exponent. So now I'm taking the 4th root of 81 over 16. Got to know your number properties. 4th root of 81 is 3. 4th root of 16 is 2. Okay, that's why I said memorize those charts from day 2 of the note sheet. Day 3. I don't know what it was. Okay, this one, it's negative. Flip the base. And it's squared. This is yesterday's work. This is actually not really today's property. It's not a fraction. Base is, but not the exponent. So now we square. Square 3 is 9. Square 4 is 16. That's it. Okay, so as I said, got to know how to do this with variables where you don't have a calculator that will skip all the steps for you and give you the answer. So look closely. This is x to the negative 2/3. First step is to make it positive. So that means we have to flip it, and then it stays as 2/3. It doesn't flip that fraction. It's exactly the same, except in the denominator. And now radicals with any positive exponents that you have. So here this is going to be 1 over, oh, what just happened? 1 over cubed root of x, and the squared either inside or outside the radical. Remember with variables, I tend to keep it inside. You can put brackets and put it outside. Next one, the base is a fraction. It's a negative exponent, so you flip the base, not the exponent. Okay. Guaranteed, if we have a multiple choice question, we'll give you an answer that has b over a to the exponent 4 over 5. But it's not. It stays as 5 over 4. So then here, as a radical, that's going to be the 4th root of b over a to the exponent 5. Again, you can put it inside or outside. Negative exponent, flip that fraction, so that's x over 1 to the 1/2. Well, what's x divided by 1? Just x, right? Anything divided by 1 stays the same. So we could simplify that a little bit. That's really x to the 1/2. So that's really the square root of x. Base is y, negative exponent, so it's 1 over y to the 1/3. So that's 1 over cubed root of y. And then the last one is an application question where we substitute a number in. So it says the time it takes a pendulum, you know what a pendulum is in physics, back and forth, yep, to make one complete swing is given by that formula, where t is the time in seconds for the swing and L is the length of the pendulum measured in meters. Determine the swing time, so that's t, for a length of 160 centimeters. So first thing, we've given you a hint here. Okay, we should have spelled that RES because we're in Canada, but whatever. That's meters, this is centimeters. How many meters is 160 centimeters, Vincent? 1.6 meters. So I'm going to convert that right now. Okay, and then I'm going to substitute it into my formula. Copy everything out. I'm just replacing L with 1.6. I'm not going to simplify anything in the bracket yet. I want to get that. I want to try to do this without a calculator. So I'm going to make that a positive exponent first. So to do that, I flip the fraction. Okay. And here's a bit of a hint. I can punch that into my calculator, right? But if I wanted to not use my calculator, I'm going to end up wanting to take the square root, right? So here, 2 pi square root of whatever 1.6 over 10 is. Well, those aren't perfect squares, but I recognize 16 is a perfect square, right? Yeah. What would I multiply 1.6 by to get 16? 10. So that would be, if I multiply top and bottom by 10 here, I would get 16 over 100. Well, that makes it easier to take square roots, right? Yeah, I'm not using decimals, I'm just doing fractions. Okay, so now if I multiply by 10, top and bottom, then now I can take that root really easily. That's 2 pi times 4 tenths, right? Root of 16 is 4, root of 100 is 10. Now, I'm not going to, I'm going to just keep pi in it because I'm not using a calculator. So what's 2 times 4 divided by 10 as a fraction in lowest terms? You can tell me that. 2 times 4 tenths as a fraction in lowest terms. Mm-hmm. Okay, yeah, just a sec. Put up your hands. Miles has his hand up. Yes, because you end up getting 8 tenths which reduces to 4/5. So this is really 4 pi over 5, and that's time in seconds. Now, if you use your calculator, you would get a decimal form, right? Because 0.8 times the decimal form of pi is obviously going to be a decimal. Okay, so that's where we're going to end.